overlying the event. What this represents is the sort of official opening of SpaceX Seattle, which is intended to be it's intended to be a significant engineering campus, and it's going to be the focus of SpaceX's satellite development activities. So in LA we have the rocket development and the Dragon spacecraft, but this is going to be the center of our satellite development activities. And what we want to do for satellites is we want to revolutionize the satellite side of things, just as we've done with the rocket side of things. And I should also say that it's possible to do a bit of both. So if you end up working at SpaceX Seattle, you can also work on rockets and manned spacecraft as well as satellites. It's not exclusively one or the other, but in terms of the sort of center of gravity for satellites will be here in Seattle. And the reason for it is pretty straightforward. There's a huge amount of talent in the Seattle area, and like a lot of you guys seem to not want to move to LA. Has its merits, by the way. So damn it, we're going to establish a significant operation here. But I want to tell you a bit about what we want to achieve with the satellites, and kind of why that's important. The satellites constitute as much or more of the cost of sort of a space-based activity as the rockets do. So very often, actually, the satellites are more expensive than the rocket. So in order for us to really revolutionize space, we have to address both satellites and rockets. And we're going to start off by building actually our own constellation of satellites. But that same satellite bus and the technology we developed can also be used for science, earth science and space science, as well as other potential applications that others may have. So we're open to both building our own as well as, we're definitely going to build our own, but it's something that we'll be able to offer to others. And the focus is going to be on creating a global communication system. This is quite an ambitious effort. So we're really talking about something which is, in the long term, it would be like rebuilding the internet in space. And the goal will be to have a majority of long-distance internet traffic go over this network, and about 10% of local consumer and business traffic. So that's, it's still in probably the 90% of people's local access will still come from fiber, but we'll do about 10% of business and consumer direct, and then more than half, I think, of the long distance traffic. As you guys may know, the speed of light in vacuum is somewhere 40 to 50% faster than in fiber. So you can actually do long distance communication faster if you route it through vacuum than you can if you route it through fiber. You can also, it can go through far fewer hops. So normally when let's say you want to communicate from Seattle to South Africa. If you look at the actual path that it takes, it's extremely convoluted. It'll follow the outline of the continents. It'll go through 200 routers and repeaters, and the latency is extremely bad. Whereas if you did it with a satellite network, you could actually do it in 2 or 3 hops. Yeah, well, maybe 4 hops. Right? Depends on what the altitude of the satellites are, and what the cost things are. But basically, with let's say at least an order of magnitude fewer repeaters or routers, and then going through space at 50% faster speed of light. So it's sort of from a physics standpoint inherently better to do the long distance internet traffic through space. And then space is also really good for sparse connectivity. So if you've got large swaths of land where there's a relatively low density of users, space is actually ideal for that. It would also be able to service, like I said, like 10% of people in in relatively dense urban and suburban environments. And so in cases where people have, sort of stuck with Time Warner or Comcast or something, this would provide an opportunity to escape their clutches. So it's something that would both provide optionality for people living in advanced countries, advanced economies, as well as people in poor countries that don't even have electricity or fiber or anything like that. So it's a real enabler for people in poor regions of the world, and it gives optionality for people in wealthier countries. So I think it's something that definitely needs to be done, and it's a really difficult technical problem to solve. So that's why we need the smartest engineering talent in the world to solve the problem. At the same time, we also make sure we don't create Skynet. Ironically, the server room at SpaceX jokingly was called Skynet. The fate has a great sense of irony. And so we really need to make sure that doesn't come true. But that's, I think, as for technically aware audience, if there's some AI apocalypse, it's going to come from some collection of sort of vast server farms, terrestrially based, not via the space-based communication system. I did think about that. Anyway, so I think this is sort of like a fundamentally good thing to do. I can't think of any sort of major downsides. It seems like it's an important thing to do. It's something that should happen. And I think it's something where properly designed could give people gigabit level access, kind of 20, 30 millisecond latency everywhere on Earth. That would be pretty great. And then that same system we could leverage to put it into a constellation on Mars, because Mars is going to need a global communication system too. And there's no fiber optics or wires or anything on Mars. So we're definitely going to need that. We're going to need high bandwidth communications between Earth and Mars. So I think a lot of what we do in developing an Earth-based communication system can be leveraged for Mars as well. Crazy as that may sound. So that's the basic story, so I'd encourage you to sort of spread the word and tell people about it that you think are great. And I should say, like, the office is going to grow slowly at first. So we're not going to sort of hire like a zillion people. So if at first, like, if SpaceX doesn't respond to you or something, please come back again in the future. It's really hard to sort of add like 500 people and all at once and have that be good. So we are going to grow it and make this like a very significant SpaceX Seattle campus, but we want to do so very carefully and kind of adding the right expertise at the right time. So if, like I said, if for whatever reason we don't get a response because our recruiting team is deluged or something like that, please reapply in like 6 months, or don't take any offense by that. So we're just trying to grow in a sort of carefully considered way. All right, I'm happy to take some questions actually from you guys if you want to just yell out questions. I wouldn't worry too much about the space junk thing. Actually we should worry about ourselves creating the space junk, but at the altitude in question, there's really not a lot out there. So we're talking about something about the 1,100 kilometer level, and there's just not a lot up there. The thing we need to make sure of though is we don't want to create any issues. So we're going to make sure that we can deal with the satellites effectively and have them burn up on re-entry and have the debris kind of land in the Pacific somewhere. That's basically what we need to make sure of. Because the number of satellites we're talking about here ultimately is around 4,000. actually technically today with discussion was 4,025, although there's probably false precision there, but that's kind of what we're thinking right now. And there's less than half that number in active satellites currently in existence. So this will be more than double the number of currently active satellites. Yeah. A timeline. Well, in the past, I've been a little optimistic on schedule. So I'm trying to recalibrate. But I think we should be able to get version 1 active in about 5 years. That wouldn't be the full sort of, doing half of all long distance and 10% of Earth's connectivity, but a useful version 1 that has global coverage, except the poles, aiming for about 5 years, and then there'll be successive versions every 2 or 3 years after that, to get to sort of get to the full. Where the system is really at its full capability is, I think it's probably 12 to 15 years. But yeah, major revisions certainly every 5 years, maybe a little sooner than that. So if you figure, in terms of major revisions, version 1, 5 years, version 2, maybe 5 years after that, version 3, 5 years after that is, rough timeline. Yeah, it's going to be, I don't know, I think quite a lot of software. All in software and firmware is probably half of the office. It's probably half software, half firmware. Sorry, half software, half software, firmware, half hardware. Yeah, so that seems like and over time the software might actually exceed the hardware number, because there's just. If we have to have something that's highly configurable, then it tends to, over time, weight towards the software. This would be not using CubeSats. The satellites we have in mind would be quite sophisticated, and there'd be sort of a smallish satellite, but with a big satellite's capability. By smallish, I mean in the few 100-kilogram range. Well, it can't be free, because then we've got a business. No, it can't be free to the user. I don't think so, because this would be. This would cost a lot to build. Ultimately, over time, to build a full version of the system, we're talking about something that would, be $10 or $15 billion to create, maybe more, and then the user terminals would be at least, maybe at least $100 to $300, depending on which type of terminal. And this is intended to generate a significant amount of revenue and help fund a city on Mars. So this is, in looking in the long term and say what's needed to create a city on Mars. Well, one thing's for sure, a lot of money. So we need things that will generate a lot of money. We're not going to, for spectrum that is omnidirectional and warp penetrating, that spectrum is extremely rare and limited. Spectrum that is not warp penetrating and that is very directional is not rare. It's sort of the difference between kind of a laser beam and a floodlight. If you can have lots of laser beams, in the limit, that would be sort of a real tight beam communication. So whereas there's high scarcity for cellular bandwidth, there is not high scarcity for space to Earth bandwidth. As long as it's not roof penetrating. So I don't see bandwidth as being a particularly difficult issue. Well, compared to the Iridium satellites, which was a sort of a mere 70, we're talking more than order of magnitude larger volume. So this is something that I think would I mean, there may be some similarities to the way that the Iridium network was done, but we would have, in terms of the production, the way it's produced, it would be closer to the way that a car is produced or consumer electronics. So we take things even a step further, and if the satellite didn't work, you just basically take it out of the constellation and deorbit it, as opposed to sort of going through this super intense acceptance test procedure to make sure the satellite works. Because normally the way satellites are done is they're like Battlestar Galactica. It's like one of them, and it's really giant. And if this thing doesn't work, it's terrible. It's like, you know, the whole business collapses. So, but if you have a large constellation, you can afford to lose individual satellites, and it doesn't affect the constellation very much. So, an analogy might be between, say, mainframes and PCs. So, if you want to have a big data center serving, you know, millions of people, it's way better to have an array of cheap PCs than it is to have a few mainframes. And that's basically how all of like the internet is served with you know, millions of PCs on racks instead of mainframes. Teaming with local propulsion companies? Not really. I don't think so. I mean, we're gonna build our propulsion unit. I mean, people in the space industry have a really difficult time manufacturing things. Like they're pretty good at designing in the first place, but they don't actually know how to make them in volume. So it's possible we could license some technology or something, but like the main propulsion system we have in mind for the satellite is a Hall effect thruster, which, I mean, not trivialize it too much, is basically like a loudspeaker. Okay, it's like a magnetic field. There's accelerating ions. It's pretty easy to make. So, I mean, there's degrees of Hall thruster, like how good it is, but at the end of the day, it's not that hard. So it's not clear that it wouldn't make sense to sort of outsource something that's not that hard. Well, there's multiple elements to the regulatory things. There's the ITU filing, International Telecommunications Union, and we've done the filings associated with that. That says whether you can actually put the satellite network up. Then there's whether it's legal to have a ground link. Obviously, any given country can say it's illegal to have a ground link, and then we can have one. From our standpoint, we could conceivably continue to broadcast, and then have a choice of trying to shoot our satellites down or not. China can do that, so probably we shouldn't broadcast there. if they get upset with us, they can blow our satellites up, which would be good. So, I mean, I'm hopeful that we can structure agreements with various countries to allow communication with the system, but it is a country-by-country basis. I don't think it's something that would affect the timeline, and at least it's not going to take longer than 5 years to do that. And not all countries will agree at first. There will be some countries that don't agree. It's fine. You know. I mean, this would be a low Earth orbit constellation, so it would actually be moving quite a bit. Yeah, so the base station would have a phased array antenna with a sort of switching time that's at the microsecond to low millisecond level. So it only take a few milliseconds to switch from one satellite to the next. So as opposed to having a dish that has a slew rate. How do you power satellites? With solar panels. Solar panels and then batteries for low Earth orbit satellites, because they go through Earth's shadow. Then you have batteries to handle when they're in shadow. Biggest concern about success? Well, I think it's important to assume that terrestrial networks will get much better over time. One of the mistakes that, say, Taldezic made was not assuming that terrestrial networks will get much better over time. So we need to make sure that the system we design is good, even taking into account significant improvements in the terrestrial systems. but I do think there are some important differences between what we're doing and say Televisic. In the case of Televisic, they were trying to talk to phones. And then that gets back to that problem of a roof penetrating situation. And it's particularly difficult when stuff is coming from space. Like if you're in a skyscraper and it's got to go through 27 floors to reach you, that's not going to happen. Like there's nothing that will, short of like a neutrino. You could have like a neutrino phone. Okay. So that in the case of Televisic, I think there are like sort of some fundamental issues there. Yeah, I think we're going to have to pay a lot of attention to security. It would really be unfortunate if it got hacked and taken over. That would be bad, whether it was by an AI or by some group of whatever. So I think it's going to be important to have some sort of low-level ROM chip that's got a code that you can always like go into a safe mode, and so it's like listening for a code, and then that ROM chip can't be updated. So it's like if you we could always trigger a safe mode situation to regain control of the system. But it's going to require a lot of thought to make sure we are able to protect it from any hacking attempts. But it's much like sort of Google and Facebook, and they handle these kind of issues. So try to answer a few questions in the back there. Yeah. So SpaceX, I think we won't take SpaceX public for quite a long time. And what I've said is, when we're doing regular flights to Mars, that might be a good time to go public. But before then, because the long-term goals of SpaceX are really long-term, like it takes a long time to establish a city on Mars. That doesn't match with the short-term time frame of public shareholders and portfolio managers who are looking at at the sort of 2 to 4 year time horizons. So I think we'll need to hold off going public for a while. Now that said, what we do is we do offer stock options and restricted stock, and we do liquidity events every 6 months. So if we have the company valued by an outside firm every 6 months, and then we will do stock buybacks every 6 months. So it's sort of, I think, gets the best of both worlds, where you have stock liquidity, but you don't have the massive fluctuations that you have with a public company, where in any given week, like for example, like Tesla, it's like any given week, it's just like it's like dealing with like a manic depressive. It's very confusing because like I'll say things that like, if people like understand what I was saying, then the stock should go up, and it goes down. Like, what the hell? Vice versa. Like, okay. So it's just, I think it's actually quite distracting to have public stock, and the time to go public ideally is when things are fairly sort of stable. Then we go public. But I think, like I said, we'll get the benefits of stock appreciation over time without the downside of going public, and then maybe 20 years from now or something like that, go public. Yeah, so there's there needs to be some sort of architecture for establishing a city on Mars, which means huge numbers of people and ultimately millions of tons of cargo. How do we do that? It really comes down to an economic question, which is there's some economic activation energy, a cost per unit mass of the surface of Mars, at which point we would have a self-sustaining civilization there, but beyond which we would not. And there's some debate as to what that might be, but I think at a personal level, there needs to be enough of an intersection of sets of people who could afford to move to Mars and people who want to move to Mars. So that's
pretty basic.
If those two coincide, then there will be a colony. Otherwise, there will not be a colony. I will eventually go to Mars. But just to sort of put that in concrete terms, I think it kind of needs to be sort of like $500,000 or less to move to Mars. Because I think that's ideally much less, but if it's much more than that, then probably there won't be a colony. So that's the basic idea. And then, so what I'll present hopefully towards the end of this year is is an architecture, a transport architecture that I think could achieve that number. So that's there's a big difference between thinking that it can achieve that number and actually achieving that number. It's like there's lots of people who suggested, hey, wouldn't it be a good idea to go to the moon? But much harder to actually go to the moon. So it's a hard execution problem. In fact, I think with most ideas, the execution is really the hard part. And in order to make that happen, you need to have lots of talented people working together towards a common goal to achieve that. So that's what we want to put together at SpaceX. All right, thanks everyone. The event. What this represents is the sort of official opening of SpaceX Seattle, which is intended to be it's intended to be a significant engineering campus, and it's going to be the focus of SpaceX's satellite development activities. So in LA we have the rocket development and the Dragon spacecraft, but this is going to be the center of our satellite development activities. And what we want to do for satellites is we want to revolutionize the satellite side of things, just as we've done with the rocket side of things. And I should also say that it's possible to do a bit of both. So if you end up working at SpaceX Seattle, you can also work on rockets and manned spacecraft as well as satellites. It's not exclusively one or the other, but in terms of the sort of center of gravity for satellites will be here in Seattle. And the reason for it is pretty straightforward. There's a huge amount of talent in the Seattle area, and like a lot of you guys seem to not want to move to LA. Has its merits, by the way. So damn it, we're going to establish a significant operation here. But I want to tell you a bit about what we want to achieve with the satellites, and kind of why that's important. The satellites constitute as much or more of the cost of sort of a space-based activity as the rockets do. So very often, actually, the satellites are more expensive than the rocket. So in order for us to really revolutionize space, we have to address both satellites and rockets. And we're going to start off by building actually our own constellation of satellites. But that same satellite bus and the technology we developed can also be used for science, earth science and space science, as well as other potential applications that others may have. So we're open to both building our own as well as, we're definitely going to build our own, but it's something that we'll be able to offer to others. And the focus is going to be on creating a global communication system. This is quite an ambitious effort. So we're really talking about something which is, in the long term, it would be like rebuilding the internet in space. And the goal will be to have a majority of long-distance internet traffic go over this network, and about 10% of